Hello everyone, my name is Dagur Ólafsson, working at IceTec here in Iceland, a research institute that was formerly Innovation Center Iceland, and today me and Béatrice Ledésert from CY Cergy Paris Université will discuss some corrosion and scaling work that we've done in the project. So, within the MEAT project, a significant part of the research works performed was the conduction and subsequent analysis of various in situ corrosion and scaling tests that we performed to find a suitable choice for heat exchangers used in the ORC power plants, as well as to evaluate some brine transport solutions. And regarding the corrosion test, what we did initially in the project was to test various coupons of various materials such as stainless steels, nickel alloys, titanium, and even plastic in different environments across Europe. Later in the project, we evaluated the corrosion of heat exchanger plates in the ORC demonstrations, which Andre already spoke to you earlier. And then we also evaluated some polymer-coated joints for transportation of hot geothermal brine and characterized scales deposits on various material candidates in two tested heat exchangers at Soultz. And during this presentation, we will discuss the various in situ tests performed. We will not go into all of the work, which would take too long time, but then we will also summarize some lessons learned. And to start with, to support Nokia with the material selection within their ORC power plants, we performed in situ corrosion testing, and in situ means then in real environment. So we placed small material samples in different geothermal environments, kept them there for a certain amount of time, and then evaluated their performance. So we looked at the corrosion defects in the samples and evaluated which materials were performing the best. And as you've seen, we mostly focused on stainless and duplex steels, but we also looked at Inconel 625, which is a nickel alloy, titanium grade 2, and even plastic. And the initial coupon corrosion testing for the, let's say, initial material selection of the heat exchangers was performed at Reykjanes, Grásteinn, and Cazaux. And then later in the project, we also did some coupon testing at Chaunoy and Soultz. And here you can see the locations of the different tests. The maps are not up to scale. Iceland is not so large in comparison to France, but as I mentioned, the previously mentioned materials were tested, and two sites in Iceland and one site initially in France, although we added to Chaunoy and Soultz later in the project. And I marked Krauma there also, since that was the ORC demonstration site, which Andre discussed with you previously. So let's go through the initial coupon corrosion testing, starting with Reykjanes, which is a geothermal area in southwestern Iceland. So there we tested all the metal material candidates in geothermal steam at 200 degrees, 18 bars for 1 month, in a special testing pressure vessel, which is operated by HS Orka at Reykjanes power plant. And there on the images on the top, you can see the samples, the two pictures on the left as they are leaving the pressure vessel, and on the right there you see them all laid out. And all the materials were somewhat affected by the testing, which is of course to be expected. And I've laid down the defects that we observed after testing, and what we were mostly seeing were various pits, some caused by the exposure itself, but what we learned during the project is also that there are various defects well, we knew this, of course, but the defects marked there are also due to manufacturing in some cases, and in some cases manufacturing defects can accelerate corrosion or be a site for pitting or other corrosion which can degrade material. But for Reykjanes, to cut it short, the best materials, the materials that performed were the best were the titanium, 254 SMO, and 904L. And then we continue to Cazaux, southwestern France, which is an oil field which is operated by Vermilion, so Eric, and there we tested all material candidates apart from titanium in an oil geothermal brine mixture at 95 degrees and 17 bar pressure for 3 months in a pig trap, which is the equipment you can see there on the top left, and you can see the samples inside there at the beginning of the test, and then the 2 images on the top right show the samples after testing. And similar as for Reykjanes, we see various defects in all of the samples, but many of them are as well attributed to manufacturing. And taking that into account, the 2 best performing materials were the 254 SMO and 904L, which are both highly alloyed stainless steels. And the third and last initial coupon corrosion testing was performed at Grásteinn, which is also an overseas demonstration site, such as Cazaux. And there on the top pictures, you can see from left to right the pressure vessel we used to test, the samples on the rack coming out of the testing, and then the samples being laid out there. And the conditions at Grásteinn were 96 degrees and very low pressure, only 1 bar. We tested this for 3 months there. And similar as for Cazaux, the best performing materials were 254 SMO and 904L, which are the highest alloyed steels there. And to recommend the material or material for a heat exchanger for Enogia's heat exchangers within the Rover C power plants, we compiled the performance, the relative performance of the various material candidates, and the results were those that 254 SMO, 904L, the highly alloyed stainless steels, and then titanium grade 2 were the best performing materials, and thus most considered for the heat exchanger plates. And as a side note, as I mentioned earlier, we did test some plastic PVF since plastic heat exchangers are used in highly corrosive conditions, specifically in chemical processing, and we decided that it might be interesting to see if it could prove a candidate for geothermal heat exchangers. But as it turns out, the plastic warped quite a bit, both at Cazaux and Grásteinn, so it was discarded as a potential candidate. And now from the first phase, the initial corrosion testing, to the second phase of the project, where we analyzed plate heat exchangers for corrosion and their material performance, as well as doing some secondary coupon testing, as I mentioned before. But today I don't think I will have time to discuss the secondary coupon testing, but we'll focus on the plate heat exchangers from Chaunoy, Grásteinn, and Soultz. So for Grásteinn, we basically, after an OGS demonstration, we opened up the heat exchanger, dismantled it, and took 3 plates from different locations within the heat exchanger, and we focused on the most affected sites. So first we analyzed it macroscopically, looking at the plates itself. Then we cut out smaller samples to analyze in optical microscopy and scanning electron microscopy. And on the right there, you can see 4 pictures from an optical microscope with some corrosion indicators on the surface of the plates, and especially the one on the top right shows some pitting occurring in the material. And so to take the results together, for Grásteinn, we observed corrosion on the heat exchanger plates, both in the form of pits, increased surface roughness, and some minor subsurface cracking. And in general, the heat exchanger plates did perform not badly, but a little bit under expectations, we could say. So it did not perform as well as expected, given the initial corrosion analysis of the coupons. But although we did see some pits and some surface roughness increase, what we should keep in mind is that the areas that we analyzed were the ones observed to be most affected, and in most areas of the plates and in most of the plates, we saw that the material was rather unaffected by the exposure. Another thing to keep in mind regarding the plates at Grásteinn is that we had in some cases, some frequent starts and stops of the ORC and some potential atmospheric intrusion into the heat exchanger flow line, which can of course increase corrosion. And although we did observe increased roughness and pits, they are in small magnitude, a few to tens of micrometers. But as you can see, though, even though on the pictures there on the bottom left, you can see quite well the notable increase in surface roughness of the geothermal fluid side in comparison to the technical fluid side. And then on the bottom right, you can see one of the largest pits that we observed on the plates. But the results here, although that 254 SMO material behaves not badly and can be used for a number of years there at Grásteinn, it does raise the question if the increased cost of more highly alloyed material such as 254 SMO does justify itself in low temperature volcanic environment when we compare it to cheaper austenitic steels such as 316L. But that's a question to look into. Now to Chaunoy. There we had a titanium grade 2 heat exchanger, which, similar as for Grásteinn, we dismantled it, retrieved 4 plates, and we analyzed them macroscopically and microscopically. And there on the right, you can see, similar as before, some optical microscopy images of the surfaces with very few minor corrosion indicators, but mostly you can see the black oil deposits, which are to be expected from such an oil geothermal water mixture. And we observed considerably less corrosion on the heat exchanger plates in the titanium grade 2 heat exchanger at Chaunoy. And the main results that we acquired were that we have mixture of deposits from the oil and precipitation of iron sulfur compounds on the surface of the titanium, which is something that we have seen previously in geothermal environment for titanium grade 2. And underneath these iron sulfur compounds or deposits, we saw some indicators of possible crevice corrosion, as you can see on the bottom left picture, although these indicators were quite minor. So in general, the heat exchanger plates performed very well at Chaunoy. Now to the final heat exchanger analysis, which was from the plates retrieved from the demonstration at Soultz. So there we removed 3 plates, and you can see the dismantling of the heat exchanger in the picture there on the left. And you can see immediately the heavy black radioactive scaling on the heat exchanger plate. You can see it's the color difference is quite significant there. And on the picture on the right, you can see some of the gathered samples which were cut from the heat exchanger plates. And due to the naturally occurring radioactivity of the scales from Soultz, which Béatrice will discuss more with you, the samples, the corrosion samples were initially analyzed at Orano in France, which is a company that specializes in the analysis of radioactive samples, before being chemically cleaned. So we removed, after analysis at Orano, all the scales were removed chemically, and also the corrosion products, and then shipped to Iceland for further analysis. So we analyzed both, let's say, uncleaned and cleaned samples, and then the surfaces, so uncleaned and cleaned surfaces of the samples, and then we did some cross-sectional analysis here in Iceland. And we noticed, well, we observed insignificant corrosion on the 254 SMO plates, which seems to resist corrosive geothermal fluid quite well. We did notice some defects, such as cracks and pits, but they were few in number. And when we observed them, like on the picture there on the bottom right, they did not reach more than about 5 micrometers into the material. But as Andre mentioned previously, the corrosion resistance of the material does not necessarily dictate the usability of the heat exchanger, as the heavy scaling formation was very hard to clean off and caused the heat exchanger to be unusable for later demonstration due to the time it took to clean it. And on that note, I would like to pass the word to Béatrice.
Thank you very much, Dagur. I will let you, okay, thanks very much. I will let you pass the slides. Thank you. So we are going to focus now on the scaling phenomenon in the heat exchangers at Soultz-sous-Forêts. Soultz is located in the upper Rhinegraben in eastern France, and the granite is harnessed at a depth between 4 and 5 kilometers. There we find brine with a high salinity, around 100 grams per liter, containing mostly sodium and chlorine, and with a temperature around 160 degrees centigrade. Next, please, Dagur. Okay, so 2 tests of heat exchangers were made at Soultz. One during 3 months in 2019, and a second one during 6 months in 2021. Several materials were tested, metals, including different alloys and titanium grade 2, as already explained by André Charles and Dagur, and also coating metals and glass fiber. The aim of the study was to test the various materials as regards scaling phenomenon in current industrial conditions, the second test, with a reinjection at 70 degrees centigrade, and second, at lower injection temperature down to 40 degrees to increase energy production. This is the test A. Second aim was to characterize the scale and check if there are differences with the different materials tested. And third aim was to see the influence of temperature on scaling. Okay, thank you. So for test A, the design of the prototype heat exchanger is as follows. The inlet is on the top. The fluid goes from west to east with a first pass, which is written 1 on the lower figure. Then it goes to the east part of the exchanger, goes back in the intermediate. Then it goes back to the outlet through the lower level of tubes. And here on the left, you have the several 6 candidates that have been tested, the different metals, alloys, and titanium grade 2. And next, please. Okay, here is what the scales look like. In fact, normally from the brine, these are sulfates that precipitate, mostly barite sulfates, but inhibitors are used to reduce the amount of scales, and then sulfide scales precipitate. So they occur as black scales, and on the lower part of the figure, you can see scanning electron microscopic views of the scales. On the left, the rough fluid side, so the side of the scale in contact with the fluid, and on the right part, it is smooth when it is in contact with the metal. Next, please, Dagur. Okay, so this is what we observed using X-ray diffraction. We see mostly lead sulfide, PBS, galena, and also on the second, on the 2 lower figures, we see also sodium chloride, which is halite. Next, please. When we focus with scanning electron microscopy coupled with energy dispersive spectrometry, we also find, of course, galena and halite. Galena is characterized by lead and sulfur at the lower part of the figure, and halite occurs with sodium and chlorine at the upper part of the figure. The left corner lower figure shows the resulting image. Next, please, Dagur. So if we look at the different metals on which the scales deposited, in fact, we find exactly the same mineralogical composition made of galena and halite, whatever the metal. We see the same mineralogy in the lower temperature tested exchanger as in normal operation conditions when the reinjection is made at 70 degrees centigrade temperature. And we tested the influence of the temperature on the thickness of the scales when the temperature decreases from 60 to 40 degrees. And we see that at 60 degrees, upper left corner, the thickness of the scale on a given metal is 50 micrometers. And you see on the top of this figure, the fluid side, which is rough, and the tube side, which is smooth. When the temperature decreases to 50 degrees centigrade, the thickness tends to increase up to 80 micrometers. And on the lower figure, we see the thickness has increased up to 220 micrometers at 40 degrees centigrade. So it was quite difficult to observe the thickness of the scales, but it seems to be a tendency to an increased thickness when the temperature decreases. Next, please. During the second test, we found exactly the same composition of galena and halite as in the first test, and whatever the metal and the material tested in general, including metals, coated metals, and fiberglass. As regards the fiberglass, I had a look at the inside surface of the pipe after cleaning and looked at it with the scanning electron microscopy. On the left side of the figure, you can see the fiberglass as the internal part of the tube as it occurs when we look at it with a scanning electron microscope. And what appears white is the deposit, which has not been fully cleaned. And when we have a look at the right part of the figure, in yellow are the glass fibers. This is silica, which appears. In blue, it is the epoxy, and in white, it is the scales composed of lead and sulfur. So it appears to be difficult to clean the fiberglass because of the fibers, which are not fully embedded in epoxy. Next, please. So if we want to give take-home messages, it is that there is no difference in the mineralogical composition of the scales, whatever the material deposited on, including metals, various kinds of metals, alloys, titanium grade 2, also coated metals, and fiberglass. And the second point is the fiberglass has to be improved in order to make it easier to clean. Well, thank you very much for your attention. If you want more information on the two studies about corrosion and scaling, you can find them in the Geoscience Meet special issue. Thank you very much.